Good morning, good afternoon, good evening. Warm welcome to all participants of SBC Virtual TechCon 2021. It's a great pleasure to be with you again. Let me invite you to the journey into the 2 decades of HIPIMS technology development. A success story, as the HIPIMS has become already a standard in many branches of the industrial applications of plasma. Let me start our journey with the picture which I like to use when answering questions, for example from students visiting our R&D lab and asking what is so interesting, what is so important in building plasma power supplies. Well, the answer is here on this picture. We are surrounded by products for which at some stage of the production plasma might be used. It might be used for plasma activation or for plasma cleaning, for plasma etching, or maybe for plasma deposition. The second question which might appear is there a space for HIPIMS in one of those applications? And the answer is yes, there is. And in this journey, within the next couple of minutes, I would like to make a short review of the most important milestones in the development of HIPIMS technology, which allowed it to be now mature and to be used as a standard tool in the mass production. Now, if we would start the discussion with the material scientist or with the process engineer about the key parameters which are decisive for the quality of the coating, we'll for sure discuss the structure zone diagram by Movchan or by Thornton, and we'll indicate that pressure will influence the ionization and the energy of the plasma, and the temperature of the substrate will influence the kinetics of the particles on the substrate. This is of course a general rule which is also valid for magnetron sputtering. However, there are applications where we cannot control the ion energy simply by changing the pressure. A good example for it is the semiconductor industry, where already in the 90s it was shown that to go with the smaller and smaller size of the structure produced on the silicon wafer, the ionization and the density of the plasma is a key factor. Development of plasma processing for semiconductor industry is interesting, but not the main topic for today. The key message from here is that not only pressure, not only temperature of the substrate, we should be able also to control the ion energy, because when we can do that, we can go from very fine structure of the coating which we deposit to the ion implantation and etching. So how to control the ionization and not to use a combination of magnetron and ICP coil to do that? Well, the idea is simple. We, instead of using a DC or pulse DC, we can use high energy pulses as we do in HIPIMS, and with these high energy pulses we can get high ionization of the sputtered species. Having said that, now we can take a look to the history of high power impulse generation, and we have to go back not 20 years, but we have to go back to 60s and 70s of the last century and the work on the Moscow Engineering and Physics Institute. In 1974, Malkin reported on their work on light sources for spectroscopy, and they have also reported a basic topology for a power supply which can run with pulses with up to 24 kA. And this basic topology, with some modifications, is used for building HIPIMS power supplies nowadays. Another milestone was the publication from the same group, from 1995 by Mosgreen, who have used such a topology for sputtering of different metals. As the political situation in Eastern and Central Europe was changing at the end of late 90s of last century, the technology transfer got easier, and this is how we were able to learn from Kuznetsov about this idea of using HIPIMS for sputtering. Of course, a natural consequence was building a power supply, as for example reported by Christie. However, to our knowledge, the first industrial size series production of HIPIMS with capabilities of 8 megawatt pulse and 3 kiloampere per square centimeters was the report by Hasharian and Buji in 2004. When Kuznetsov introduced his patent and papers, he focused on the semiconductor industry. He was able to show that the combination of HIPIMS and bias can be used for a moderate, as for that time, aspect ratio of the via structure on the silicon wafer to coat this structure with metal and get a fine structure of the coating. After more or less 20 years, the requirements of the semiconductor industry are much more rigorous. Now we are talking about aspect ratio of 40:1, so we are talking about high aspect ratio. Also here, as we showed in 2017, HIPIMS has a potential to be used to produce a homogeneous, high quality titanium copper coating, as you can see here on the side walls of the via and also on the bottom of the via, where we get a uniform metal coating. This shows that HIPIMS can really be used as a trigger for new technology development. The availability of the industrial size HIPIMS power supplies already in the first decade allowed not only to show the clear difference in the ion energy as compared, for example, to DC plasma, where we could increase the amount of highly energetic ions in the spectrum by using HIPIMS. But by this we could also change the plasma composition when using HIPIMS and to decrease the amount of the base argon gas in the plasma and increase the metal ions as well as the doubly or triply ionized metal ions. And this in turn has the dramatic influence on the structure of the coatings, as shown here for DC sputtered layer. It's clearly developed with voids, it's clearly columnar and a rough surface. However, with HIPIMS, as we see here, it's a densified and hard homogeneous coating. It's almost columnar free and smooth. Another field where HIPIMS already has proven its advantage is the interface between the substrate and the coating. The coating adhesion problem is one of the biggest nightmare of the process engineers. The adhesion problems can be related to the stress in the film, but it can be also tuned by applying an adhesive layer between the substrate and the coating. So the transition layer between them, which will bond the coating to the substrate. By using such technology, it was shown that we can change the interface between the substrate and the coating and get coatings of bulk material density without any voids between the substrate and the coating. But this is strongly related to the plasma generation and biasing technology which we will use. And already at the beginning of the using of HIPIMS in the industrial size systems, it was noticed that a standard bias is not enough. Why? Because if you would have a current spike, the bias power supply will detect it as an arc, and instead of having 8 volts applied, as in this case, you will end up with maybe 50 volts, because the power supply will see it as an arc. On the other hand, you would need a special designed HIPIMS bias, which can take a high current spike, which will be generated during the HIPIMS pulse, and it will maintain the voltage constant during the operation. It will not only give the stability for the power supply operation, but it will also give the stability to the quality of the coating. Another advantage of HIPIMS is also related to the quality of the coating. There are processes using cathodic arc pretreatment. The processes are even much older than processes with HIPIMS. And with those you can also get a decent quality of the coating, for example used for the cutting tools. However, these coatings are always having the problem with defects from macroparticles in it. And to change this situation, you could use the HIPIMS pretreatment, which will also give you high ionization of the plasma, but you will get a coating without such defects from macroparticles. Why is it so? It's because that already from the beginning of the HIPIMS technology, of the generator technology, the detection of the change of the electric discharge regime from glow discharge, which is typical for HIPIMS operation, to the arc discharge is controlled by arc suppression methods. What does it mean? Well, typically we are operating somewhere here. So as an arc occurs, what happens is that the voltage will drop down and the current will increase. So we'll shift from here to this region. So we'll have low voltage and high current. And this is what triggers formation of macroparticles. So what is happening in the power supply? As soon as the current increases and the power supply detects an arc, it shuts off the pulse and the formation of macroparticles is stopped. In order to define next steps in HIPIMS power supplies development, important was to take a look not only on the coating properties, but also to include the plasma properties as well as the deposition process properties. And it was shown already in 2002 that the shape of the voltage and current pulse influenced the optical properties of the plasma. It influences also the dynamics of the ions which are arriving to the substrate. Furthermore, it has been also discussed that control of the frequency of operation can influence the, so to speak, the holy grail of the HIPIMS operation, so the deposition rate. And finally, the deposition rate can be also influenced if we are able to control the peak current of the HIPIMS, and then we are able to control the deposition rate not only in the metallic mode but also in the reactive mode. A natural step in the development was therefore to change from the triangular shape of the HIPIMS current pulse to the rectangular one, in which we are able to maintain a constant current during the pulse. Such a change has been shown to have a dramatic influence on the plasma chemistry. Here we are presenting a OES signal recorded with a rectangular shape of the HIPIMS pulse in a argon-oxygen mixture of gases on the titanium target. the pulse is 100 microsecond long, and if we zoom in to this part of the pulse, we see that through all the pulse the intensity of the both argon and oxygen is increasing, as we see here. But what is even more important, the intensity of the titanium ions is also increasing through all the pulse. This is one advantage. The second one is also the possibility to tailor the deposition rate. And already in 2014-2015, with the second generation of these power supplies with rectangular shape of the current, we were able to show that it is dramatically increasing the deposition rate by factor almost of 2. And this is the very important advantage of changing the shape of the HIPIMS pulse. Another advantage of having a control current during the HIPIMS pulse is the possibility to enter the bipolar operation. Many industrial systems are systems operating with dual magnetrons, both planar and also rotary magnetrons. And those systems need HIPIMS which can work simply in a bipolar operation mode, as MFs or bipolars which are known in this community. So we can not only improve the quality of the coating by introducing HIPIMS, but we can also enter the possibility of material mixing with bipolar HIPIMS operation. And the ultimate goal would be to finalize the testing in the large area coating, where HIPIMS can be also applied, for example, in some low E coating business. In previous slides, we have already discussed how important is the cooperation between the HIPIMS and the HIPIMS bias power supplies. In 2012, Greg Gajewski published a very important paper in which he and his co-authors showed that if we can use a pulse bias and we can shift it with respect to the HIPIMS signal, we are able to tune the properties of the coating. This solution has been already tested in the industrial size systems, and indeed the shifting of the HIPIMS pulse bias with respect to the HIPIMS does influence the quality of the coating. And this brings me to the last point of my presentation, to multi-synchronization, a new paradigm of coating system configuration. As you might know, the systems which are operated at the moment might be equipped with different power supplies for different process steps. It might be a HIPIMS operating on a single target. It might be a HIPIMS operating on dual target, or it could be also combined with different power supplies, including the bias. Connecting all of those power supplies in a kind of network, it's not only bringing the elimination of arcing, improving the arc recipes, or including the selective bias, but also opening new possibilities, for example, in the future applications of IoT readiness. To conclude my talk, I would like to emphasize 3 key messages. First of all, the HIPIMS is mature, flexible, and ready to be used in different branches of the industrial application of plasma. Secondly, it gives the long-term stability also in the processes with high arcing rate. And third, the synchronization between different power supplies opens new possibilities for the future applications. I would like to acknowledge all the cooperations and contributors to this talk. And finally, thank you for your attention. Thank you very much.